I want you to try something for me. Look up from whatever you're doing right now. Look at the wall across the room, or, maybe a building out the window. If you're driving, look at the car ahead of you. Now, here's the question. Are you seeing those things right now?
That's a trick question, isn't it?
It feels like a philosophy question, right? What is the nature of the present? But today we're finding out that it's actually a really stubborn geometry problem because, strictly speaking, you aren't seeing now. You never have. You are looking at a map of the past.
It's a heavy way to start. But you're right. We tend to think of our eyes, and by extension, the cameras we build and the physics equations we write as these like instant
We
scanners.
just assume we capture the world in real time.
Exactly. But the source material we're deep diving into today argues that we are fundamentally camera eyes. We're stuck at a specific point in space staring at a monitor that is playing a delayed broadcast.
And that delay isn't just some tiny lag. The argument here is that this delay is responsible for some of the weirdest stuff in physics. Today, we are unpacking a really unique stack of sources. We've got a series of dense research notes, logs from conversations with an AI model named Gemini, and this is the part I love, a Python script written for Blender.
Blender, the 3D modeling software.
The very same. We're going from high-level theoretical physics to actual code debugging.
That is an unusual combination. I mean, usually we're looking at peer-reviewed papers or history books.
Exactly. And the mission is bold. We are exploring a new geometric model, the unit circle or complex space model, and the big claim that things like length contraction, objects physically shrinking when they move near light speed, might not be physical changes at all. They might just be misunderstood effects of that information processing delay.
So wait, instead of the universe getting weird and squishy at high speeds, it's just our video feed lagging.
That's the hypothesis. But before we get to the code, we have to talk about this camera eye. The source uses an analogy of an information officer sitting inside your brain.
I like this analogy. It grounds the math. So imagine a standard coordinate system, the grid we all learned in high school. Usually classical physics assumes a God's view. That means we assume we know where everything is on the grid at time zero instantly. We pretend we can see the whole board at once.
Right. But the source says, no, you can't be everywhere. You, the observer, are sitting at a specific point. Let's say coordinate 0, 0, 0. Or, to use the source's specific example, imagine you are sitting at Y10, looking at a giant screen at Y0.
Okay, so I'm the information officer. I'm sitting back at -10, and I'm looking at a wall 10 meters in front of me.
Simple enough. Now look at the floor. Then look at the ceiling. The source points out something really obvious, but so easily ignored. The floor is right in front of you. The light travels a straight line to get to you.
Right, distance is 10 units.
But the ceiling, you have to look up. That's a diagonal line.
Oh, okay, wait. I think I see where this is going. Pythagoras. The diagonal is always longer than the straight line. If the wall is 10 meters away, the path to the ceiling might be, say, 14.1 meters.
Correct. Which means the light from the ceiling takes longer to reach you than the light from the floor.
So if I'm the information officer, I'm getting the news from the floor faster than the news from the ceiling.
Exactly. But your brain, that monitor in your head, it stitches those two signals together into one single picture. You think you're seeing the room all at once, but you aren't. You are seeing the floor as it was 10 seconds ago and the ceiling as it was 14.1 seconds ago.
It's a patchwork, a collage of different pasts.
And here's where it gets trippy. What happens if that room is moving?
Well, if the room is moving, and I'm seeing the ceiling from further in the past than the floor, then the ceiling was in a different physical spot when it sent that light compared to where the floor was when it sent its light.
Boom. In your monitor, the room looks tilted. It looks distorted. Not because the room actually bent, but because you are stitching together data from different times.
And this is the crux of the argument, isn't it?
Mm.
The source claims that traditional physics, specifically Lorentz contraction, saw this visual distortion and decided it was a physical reality.
They saw the tilt and said, the object has shrunk. The geometry of the object changed.
Instead of saying, oh, that's just a processing artifact because the ceiling is further away.
That isn't a massive distinction. We're talking about the difference between a car looking small because it's far away versus the car actually shrinking to the size of a Matchbox toy just because it drove away from you.
So if the flat wall view is the problem, because the corners are further away than the center, how do we fix it?
The notes talk about a unit circle.
Right. To fix the delay issue, we need a shape where every single point is exactly the same distance from the observer.
A circle.
Start with a circle, yes. Imagine you're at the center. The circle around you represents a specific moment in time. Let's say the radius is 300,000 kilometers of light second. Every single point on that circle is exactly 1 light second away.
So if I look at that circle, I'm seeing everything on it with the exact same delay. No mix and match paths.
Precisely. It's what the source calls the isochronous promise. But of course, we live in 3D space, right? So you have to upgrade that circle to a sphere. You are in a bubble.
Okay, I'm in a bubble.
And the force refers to this circus as the spherical cap. In standard relativity, people talk about light cones, but usually they draw the past as a flat slice. This model argues the past is actually a curved dome surrounding you.
A dome of then?
Yes, and this curvature matters because when you try to take a straight object like a train and view it through this curved lens of time, weird things happen.
Let's talk about the train. The notes call this the line train versus the arc train. You know, I have to admit, I had a little trouble visualizing this at first. Why does a straight train become an arc?
Think of it this way. Imagine you are holding a long, straight ruler right in front of your face. Hold it horizontal.
Okay, so I'm holding a ruler right in front of my nose.
The center of the ruler is, say, 10 centimeters from your nose. But the ends of the ruler, they are further away to your left and right.
Right. The diagonals again?
So if you were plotting time delay on a graph, the middle of the ruler has a short delay, a low point on the graph, and the ends have a long delay, the high points. If you connect those dots, that straight ruler looks like a curve, an arch.
Oh, I get it. Physically, it's a straight line. But informationally, it's a curve because the ends are deeper in the past.
Correct. The source calls this the observer's dilemma. If a train is 20 meters long and moving at 10% the speed of light, you aren't seeing the train as a single object. You're seeing the front from a newer past and the back from an older past. You're seeing a smear of time.
And the source says we should treat this as an arc.
Yes, they perform a complex space transformation.
Mm.
Instead of trying to force the train to stay on a straight line in our math, we map it onto that unit circle. We accept that the data is curved.
There's a really poetic line in the notes about this. It calls the observer a half-ghost.
I highlighted that too. It's a great image. It says half of the observer is the abstract mathematician at 00, the mind that understands the geometry. The other half is the physical body at the edge of the circle actually receiving the light.
And the gaze connecting them is the umbilical cord. It feels surprisingly human for a physics discussion. It's acknowledging that we are split between what we see and what we know.
Which brings us to the most controversial part of the notes, the section titled The Cheat of Simultaneity.
Yeah, I wanted to ask about this. The source accuses Einstein and Lorentz of sabori.
It's a Japanese term. It roughly translates to skipping work or slacking off.
That is a bold claim. I mean, we are talking about Albert Einstein. Are these notes really saying Einstein slacked off?
In a specific mathematical sense, yes. The argument is that Einstein and Lorentz skipped the procedural geometry we just talked about. They treated the coordinate system as a rigid box rather than a projection screen.
How so?
They ignored the ma'ai.
Ma'ai, isn't that a martial arts term like engagement distance?
It is. In kendo or karate, ma'ai is the critical interval of space and time between opponents. You have to respect the gap. The source argues that Einstein treated the window, the screen, and the eye as the same thing. He ignored the depth between the observer and the event.
Give me a concrete example. How does ignoring this gap mess up the physics?
Okay, look at the famous train paradox. Standard relativity says, imagine you are on a moving train. You turn on a light in the center of the car. For you, inside the train, the light hits the front wall and the back wall at the exact same time. Simultaneous.
Right, that's the textbook definition.
But this deep dive source says, false.
False.
False. If you acknowledge the electromagnetic field, what they call the Maxwell C,
Okay.
think about it. The train is moving through the field. You flash the light. The light expands in a circle. But the train is moving.
Okay, so the back of the train is moving into the light.
Yes. The back wall is rushing toward the spot where the flash happened. It catches the light sooner. The front wall is running away from the flash. It catches it later.
So they aren't simultaneous, even for the guy on the train.
Not in the absolute sense of the field geometry. But here's the cheat. To make the math work, to make it look simultaneous, for the passenger Einstein had to tilt the plane of simultaneity.
He tilted the math.
He effectively treated the future of the front of the train as the present. The source argues this was a mathematical trick, a sabori, to hide the speed difference. By ignoring the processing delay, they had to warp space and time to make the equations balance.
That is, well, it's unsettling. Because relativity works. We use it for GPS. The satellites have to account for time dilation. If Einstein cheated, why does the GPS still work?
That's the million-dollar question. The source admits the math works as a predictive tool, but it challenges the interpretation of why it works. Is it because time itself is warping? Or is it because we've built a system that perfectly accounts for the information delay, just using the wrong labels?
And this is where we leave the chalkboard and go to the computer. Let's talk about the Blender script, version 5.7.
Relativity Sim v5. This is where the rubber meets the road. It's a Python script written to simulate the Michelson-Morley experiment inside a 3D engine.
For those who slept through physics class, give us the 10-second refresh on Michelson-Morley.
Sure. Late 1800s. Scientists thought light traveled through an invisible substance called ether. They built a device, an interferometer, to detect the ether wind as Earth moved through space. They split a beam of light. One arm goes forward and back, the other goes up and down.
And they expected the light moving into the wind to be slower, but they found nothing. The speed was the same.
Right, the null result. And to explain that, Lorentz and later Einstein said, well, the arm of the device facing the wind must have physically shrunk to hide the delay.
Length contraction.
Yes. Now enter the Blender script. The source notes mention a specific bug fix in the code regarding the y-axis arm, the one going up and down.
What was the bug?
It's fascinatingly simple. In the early version of the simulation, when the mirror moved, the code just calculated the light going straight up and straight down. But think about it. If the mirror is moving sideways while the light is in the air...
The light would miss the mirror.
Exactly. If you throw a ball straight up while running, it lands behind you. To catch it, you have to throw it at an angle. You have to throw it along the hypotenuse.
So the coder realized, wait, my light vector is wrong.
They had to fix the vector to account for the diagonal path. And when they updated the script to version 5.7, something magical happened. They discovered time balance.
Time balance. Is this a new formula?
It's a derived one. Tau plus 10 equals a constant.
Break that down.
It means the time it takes for the signal to go out plus the time it takes to return balances out perfectly, regardless of the angle or the motion.
Wait, if the time balances out naturally...
Then you don't need the device to shrink. The interference fringes don't change because the information delay balances itself out. The math shows that if you account for the delay properly, using that hypotenuse path and the unit circle geometry, the anomalies that led us to invent special relativity just dissolve.
So the weirdness of physics time slowing down, objects shrinking, was just a bookkeeping error.
A bookkeeping error caused by ignoring the diagonal path of information. We forgot the my.
That makes the universe feel, I don't know, sane. It's less like a magic show where space bends and more like a very orderly, very strict postal service.
It shifts us from a physics of absolute places to a physics of information procedures. It's not just about where the electron is. It's about when the news of the electron reaches you.
It changes how I look at the stars. I mean, we always say, oh, that star is a million years in the past. But this model says, no, the coffee cup on your desk is in the past. Your hand is in the past.
Everything is a map of the past. We are that information officer trapped at 0, 0. The source uses that image of the spherical cap again. We aren't looking at a flat picture of now. We are inside a dome plastered with postcards from then.
It's a bit lonely, isn't it, being the half-ghost at the center?
In a way. But it's also empowering. It means our perspective defines our reality. When you move, you aren't just changing your location. You are rotating your entire unit circle through the data stream of the universe.
So does now even exist, or are we always just watching a delayed broadcast?
In this model, now is just the processing event in your brain. The universe out there. That's always gone by the time you see it. We are always inevitably late to the party.
But at least now we have a better map of the party.
We do. And I think what's most exciting about this deep dive isn't just the physics, it's the method. We used a 3D graphics engine, a tool for artists, to solve a problem that stumped physicists for a century.
Because they were drawing lines on paper, and we can simulate light paths in 3D.
Exactly. They had to imagine the line train. We can build the arc train in Blender and watch it fly.
Always question the coordinate system. That's the takeaway for me today.
It's a good rule for physics, and probably for life too.
I'm going to be thinking about that arc train every time I take the subway now. Bending through information space.
Just stop thinking about the moth.
I'll try not to. And to you listening, thank you for joining us in this complex space. Next time you look out the window, remember, you're not seeing the world as it is. You're seeing a map of time. Thanks for listening to the deep dive.
See you in the future.